In the name of God, my name is Zohreh Torki. I'm master student of computer networks in Yazd University. Our article is about optimization resource allocation in NOMA-based for computing with a hybrid algorithm. Internet of Things networks are large graphs with multiple nodes and different resource capacities that influence resource allocation strategy to provide the desired quality of service in applications. Management and resource allocation in IoT systems have been discussed as an essential research topic for years. The dynamic and heterogeneity of resources make resource management a challenging issue for the Internet. Another problem with IoT is the shortage of processing and storage resources. This problem has been solved with the cloud computing. Cloud computing has unlimited storage space and high processing power, but delay in sending and receiving information is one of the main problems of this system. Also, the current bandwidth and cloud architect don't respond to this amount of data. Fog computing solves this problem by placing between the clouds and the nodes. Fog computing is a distributed infrastructure that provides computing resource storage and network services at the edge of the networks. Although fog computing reduces data processing delays, it creates a challenge in allocating resource with the quality of service needed. Some of the advantage of using fog is reducing sending data to the cloud, reduce response time, save bandwidth, and increase security. Due to the limited resources available in the IoT, resource allocation affects the performance of fog nodes. With the help of resource allocation algorithms, tasks are mapped to suitable nodes. Choosing a suitable and efficient algorithm can be effective in improving the performance of the IoT network. The dynamic nature of the network environment and use the frequency band at the same time with NOMA has led us to move to meta-heuristic algorithms to solve optimization problems in the fog environment. So we can use them to make the best decision in terms of offloading tasks to the fog nodes and allocating resources. One of the most popular exploratory techniques used to optimize complex problems is the genetic algorithm. The genetic algorithm use evaluationary operators to find the optimal solution. Initially, chromosomes are randomly generated to represent different solutions. Genetic operators are then applied to weak chromosomes and produce new children for the next step. The genetic algorithm only needs information about the quality of the solution created by each set of variables. Gary-Wolf is another new meta-heuristic algorithm for solving optimization problems that are inspired by the group life of wolves and how they hunt the wild. The Gary wolf can detect the location of prey and surrender it. The hunting process is usually led by alpha wolf. Beta and delta may also occasionally hunt. The main phases of Gary wolf hunting are as follows. First step is tracking, chasing, and approaching the prey. Second step is harassing the prey until it stops moving, and the final step is attack toward the prey. In this article, we consider a general system model in IoT networks. Heterogeneity sources are considered jointly in different devices and fog nodes. Fog nodes are deployed to serve IoT devices. The entire frequency band is divided into resource blocks, and many users can use the same resource at the same time with NOMA. The generated data may be processed locally or by fog nodes. In the local computing approach, tasks are processed by the IoT resources. The processing delay of each request in the IoT device is calculated from following equation that CL is the amount of data processed locally, and FAL is calculation capacity. Limited local resources, delay sensitive tasks are sent to the fog nodes for processing. In this way, it will be an additional overload to transfer data between IoT devices and fog nodes. The delay of transferring tasks from device to fog node is calculated from this equation, where Cin is the amount of data input to the fog node, BW indicated the downlink bandwidth that the fog node can use to receive data. D is the distance between the IoT device and fog node. P is the IoT device transmission power, and N is the noise power spectral density. The processing delay of each request in the fog nodes is calculated from this equation, where CF is the amount of data processed in the fog node. In this article, we formulate an optimization problem to reduce energy consumption and system latency in IoT networks with NOMA. The decision of offloading, resource allocation, and transmission power are formulated as a complex problem that is solved using two algorithms, Gray-Wolf and genetic. The first part of this equation is the energy consumed in local processing for task N of device M, and the second part is the energy consumed in sending to the fog node, transfer to fog node, and processing in it. C cycle is the number of CPU cycle required. PMOK is transmission power, and BMOK shows the result of resource allocation in binary. To solve the optimization problem, we propose a new hybrid algorithm based on the strength of the Gray-Wolf algorithm and the genetic, in which offloading and resource allocation decisions are considered jointly. In order to improve the performance of Gray-Wolf during prey attacks, we increase the effectiveness of alpha solutions and decrease the effectiveness of delta solution to improve random neighbor search. For this purpose, by weighting the wolves and applying more weight to the alpha wolf, we give more value to the best answer. In other words, the alpha has the most weight during the hunting process, followed by the beta wolf and the beta wolf. Since the response space is searched extensively in the genetic algorithm, there is a less probability of converging to the local optimal point. For this reason, after implementing Gray-Wolf algorithm, the response are updated through genetic operators to allow exploration of new space and not get caught in a local optimization. This approach is such that after updating the position of the wolves and before completing the repetition using a loop, it can be determined that we intend to apply the mutation or crossover operator to the answer several times. Experimental results show that we improved equation of updating the position of wolves and merging two algorithms can effectively balance the speed of discovery and convergence of the algorithm. In this paper, MATLAB used to evaluate efficiency of the proposed hybrid algorithm. This section discussed the effect of the number of device, resources, and tasks on energy consumption. The results show when the number of tasks and devices is constant, more devices consume more energy to convergence. And when the number of devices and tasks is constant, more resource mean more transfer resources for offloading, which improves convergence performance and reduce energy consumption. Similarly, when resources and devices are constant, the energy required for convergence increases as tasks increase. In this section, the average delay of the proposed algorithm is compared with two problem-solving modes by the genetic algorithm and the Gary-Wolf algorithm. In the proposed method, due to the use of NOMA and the possibility of sending requests to the fog node at the same time, as well as using the positive points of two algorithms, the delay of tasks compared to the separate execution of each has been reduced. In this part, the convergence performance of the proposed algorithm is compared with the genetic and the standard Gary-Wolf algorithm. According to the result, the genetic algorithm takes longer to convergence and isn't caught in the local optimization, but the Gary-Wolf algorithm converges more quickly and is more likely to be caught in the local optimization. The proposed hybrid algorithm, in addition to maintaining the execution speed, has better convergence than other compared streams, and also has the lowest energy consumption by assigning tasks dynamically to IoT device and fog nodes according to available resources. In this paper, we introduce an improved hybrid algorithm to solve the NOMA-based resource allocation optimization problem. The hybrid algorithm proposed to improve global and local search by modifying the standard Gary-Wolf algorithm and combining it with the genetic algorithm. The approach is that after updating the position of the wolves and before compiling the iteration, a loop can be used to specify how many times the mutation or crossover operator is applied to the solutions. The simulation results show that using positive points of two algorithms has led to improved latency and energy consumption compared to the separate implementation of both algorithms. Changing in the local and global search method in the proposed algorithm has caused a balance between exploration and exploitation in addition to reducing latency and energy consumption. Thanks for your attention.